Today we're going to talk about Einstein's theory of relativity. Now, if you've ever listened to how they discussed it, one of the ideas that Einstein had was, if you have a clock, like right here, and you have another clock in your pocket, like what we have here, and you start to travel, boom, and you travel at the speed of light. Now, if you can look back at the clocks behind you and you're traveling at the speed of light, what his theory was that the clock would stop. You know what? I agree with part of that. Part of the idea is you're traveling at the speed of light. The light is traveling the same speed as you. The observable time stops, not time itself. And I'm going to show you why. Now, if you have a GPS, how does it work? Does it work with two satellites? No. So if you think about Einstein's theory of relativity, he has 2 points of reference. The one you're going from and where you're at now. So how do you figure out where you're at with the GPS? You have to have 3 points of reference. It's a simple, very simple geometrical thing that's used. It's called triangulation. It's geometry. You have 3 points of references to figure out where you're at. So let's do that. Let's triangulate Einstein's theory of relativity and see if it's true. So you're starting at point A right here. You're going to go over here to point B. It is 1 light hour away. You have a clock here at 12. The clock in your pocket is also 12 o'clock. Since this is 1 light hour away, it takes an hour for the light to get there. So what does it say? It says 11 o'clock. It's an hour behind. So now, as you travel at the speed of light, boom, off you go. So if you go a half hour, what Einstein says is the clock behind you, the observation of that time, does stop. The light's traveling the same speed as you. You can't see it move. So if you travel a half hour, like so, what happens to the clock in front of you? Right? You're traveling at the speed of light. You're moving half the distance there, so half the observable time. The clock in front of you, the observable time of the clock in front of you, will go how fast? Twice as fast. So what happens here is this clock here now will go 1 full hour. The observation halfway there. So then if you travel another half of a light hour, what happens to the clock behind you? It still stops. The clock in your pocket spends another half hour. And what happens to the clock in front of you? Spends 1 more hour, spins twice as fast. So what happens? Both these clocks are now at 1 o'clock. Very simple triangulation. So now you're here and you want to go back. So you take off at the speed of light. You go a half an hour, like so. The clock behind you stops, just like Einstein said, but the clock in front of you that you left now, what happens to it? It goes twice as fast. Now, you go another half an hour, another light half hour, traveling at the speed of light. The clock behind you stops, just like Einstein said. The observable of it stops. This one then will go another, spin twice as fast, and spin 1 hour. So now, you went a light hour away, a light hour back, and what happens to your time? They are exactly the same. Time did not change. When you arrive here, both clocks say 2 o'clock. What stopped? The observation of time. The observation. Because now look here. You're 1 hour behind here. Not really. It's the observation of it, because it takes it an hour for the light to get there. It's the observation of time that stops, not time itself. That's all you have to do to disprove Einstein's theory of relativity is use simple geometry, triangulation. Everybody knows you need 3 points of references with your GPS. If you have 2, you have no idea where you're at. So why do you not know where you're at on the theory of relativity? Because you're using 2 points of references. Use 3, apply it to the theory of relativity, and you'll see it just falls apart. Why is that? Why is this so easy to explain? It's because physics and chemistry are easy with the correct geometry.